Good afternoon, good morning. Thanks for showing up for day two. So we'll pick up where we left off. If you remember, we introduced the notion of ground state for an infinite quantum spin system. So we had our balance, the algebra of observables, the interaction that defines the dynamics with good interactions, you get nice dynamics generated by a generative delta. You can write it takes the place of trying to integrate the Hamiltonian in the finite system. And then the state omega of the gamma in the ground state for the interaction P if you have the following omega is delta A equal to 0 for all A in the domain of that derivation that generates the next event. In all cases, we will consider to assume that that domain includes the algebra of local observables. And in fact, so it's well known that for finite phase interaction, that's a core. We assume that it's the core where some of the arguments that are in any case, I will go into. Okay, so you can verify this under very general conditions just for the local observables and the equivalent. So, as a motivation, I gave out this definition. If you apply it to finite system, is equivalent to the well-known physical definition that either the vector or the density matrix representing a state is supported eigenvector of the finite quantum Hamiltonian small eigenvector, the million energy states. And there's some other good ways to motivate it. The good one is to look at the GNS representation we'll need anyway, and which Peter, in fact, is using extensively in his lectures. So let's quickly recall what that is. And then look at some basic properties that give us confidence going forward. So this GNS representation exists for any state of the C-star algebra. And so we are interested in the gammas, which are observables for the spin system that in fact general. So that's formulated in general language. Theorem due to Gelfand line Siegel. So that A be any C-star algebra. State A. Then there exists the Hilbert space. H omega. For now, I will indicate dependent on the state omega. Systematically until I get tired of doing it, and then we'll drop it. It is. It's there. A unit vector. Capital omega in the Hilbert space, and in the representation I omega of the algebra. About linear operators on the Hilbert space. So far, there's no connection between omega, the state, and the this representation, but here it is. So with the following properties. So first of all, the expectations of our observables can be computed in something that looks like the original finite system quantum mechanics. We take the expectation and the vector state. It's unit vector omega of representative omega representation. And then the other property is that if you act with all vectors representation omega and the vector omega, you get that subspace of your vector space. So that's very good. It looks like we have just something we are familiar with in quantum mechanics. There's many different representations that you can use. They're usually in finite systems related by unitary transformation. This is not the case here in general, but otherwise it's pretty much the same idea. It's the algebraic relation between observables that matter. But take a representation. I'm talking about the same system, but the state can be presented as a state. So the second property is important to kind of make this representation unique. So it's canonical in a way. In the following sense, to lead up to unitary derivatives, any two such representations so I'm going to denote it by triples. So there is a vector space. Now I have two vector spaces, and I have two vectors, two representations. So I is 1 or 2. And assume that it satisfies these properties. So then one vector space 1 and the representation 1, and the 2 have these the same properties. Then you like meaning that there exists a unitary element U. And then next from H1 to H2, or from H2 to H1, I just to make sure I write my formulas consistently with what I said. So unitary from H1 to H2, such that omega 1 is mapped to omega 2, and the representation pi 1 is unitary equivalent in the sense that I conjugate U by 2 and I get pi 1. So make it all part of the same theorem. I'm going to prove it. Many texts gives you proofs. I think I have to prove it. The lecture. Oh yes, by the way, I prepared the file with references for at least the first couple of lectures, and then I'll add to it. So maybe I'll email it to Anton. He will find out how to get it. Is that good? Yep. Yeah. All right. So in fact, the unitary itself, that if you have two such representations, the unitary itself is also unique. I mean, that's kind of easy to see because it has these properties. It maps directly vectors in that subspace in one to specific vectors in the image, and therefore it is uniquely determined. Okay. So very important theorem. It's often sort of considered as sort of the beginning of the theory of representation theory, C-set algebras. One way in which it was very important. Because it showed me that you have a lot of representations of C-star. At least if you have a lot of states. In many cases, you know how to define states. So for any state, there is a representation. Now, for finite systems, our algebra of observable is just a matrix algebra. There's only one irreducible representation. It's a square matrix algebra. So this is very different when you go to the infinite system. There are many, many representations, and some may be unitary equivalent, but there's also many elements. And this is directly related to what we're trying to do when we say we want to classify states, maybe graph states according to certain fundamental properties, and certainly all the ones that are unitarily equivalent, we would want to put in the same class. Okay, so I'll give you directly now an application. So similes in quantum mechanics and in finite systems again are given by unitaries that commute with Hamiltonian, commute with the interaction of defined Hamiltonian. You can also define the observables as an automorphism. And for finite systems, that's the same thing. Every automorphism is of that form. But in finite systems, similes will be presented. So it's automorphism alphas, and then the fact that I have similes of the dynamics will be statement that the dynamics commute to that automorphism. So again, if you go to infinite systems, you can have automorphisms that commute to the dynamics or the stated value. It's not clear, but it's by unitary. But there's something interesting if you have a valid state. So here is an important proposition. You look at right there. So you can, this is all true more generally than just in the quantum spin system situation. So I'm not going to write it all down. But if the state omega we were talking about this is invariant under the automorphism. So you compose it in this unitary transformation finite system of the automorphism system. Then alpha is implemented in the GNS representation. And so this means there is a like that will show exactly what it means. And so the proof is very simple. So you have the GNS representation H omega pi omega, and now consider another representation, same Hilbert space, same vector. If you compose the representations in that automorphism, it gives you another representation. And of course, so this is actually a representation of the same state, because omega of k is omega pi. And omega of alpha, which is equal. So I can write this here. Okay, so I have exactly all the same properties. And since this is actually the same as that, it's just another representation with the same properties as the GNS representation. It's a GNS representation. It's therefore unitarily equivalent by the unitary uniqueness. Okay, so And the other space is the same. So this H1 and H2 are both equal to H omega. And so there exists the unit of H omega such that these two representations are related. And when I say about U, I can say about U star. Since of course omega is invariant alpha, it's also invariant with alpha English. It's an alpha basically on the way. Thank you. So this is what we mean by unitary momentum. The action on the observable algebra by automorphism becomes the adjunct action on the unitary interaction. So by the way, also something Peter mentioned that these algebras here, they gamma, your fit system are simple, and so only this means that the only irreducible representations are really isometric copies of the algebra. We get to the algebra but the representations don't have to have this property. But in the United States, you can implement. So this automorphism doesn't have to be in. So there doesn't have to be a unitary in the algebra that satisfies this relation. So I cannot put a phi of some unitary in here and have this relation. I have to go to the representation. So a good case for using the GNS representation on some wire. Okay. So maybe you remember, you don't, but to remind you, I made a claim that the United States either should be stationary states as we have finite systems. This is expressed by the factor omega of delta A. This is the derivative of omega delta A 0. And so this is equal to 0 for all A in right, that means that omega is the value of that's simple ground states. Okay. So that means that for every t, dot t is the symmetry of the state. And we can apply that proposition. Apply the proposition. This is the unit. Unity. I can know the GNS of the space that implements the time so that phi omega of tau image is in fact UT star UT and UT omega. So the time evolution turns out that in this representation is represented practically in the same way as we had it during evolution for finite systems. Where you define the unitary as the unit. So now we have the unitary. It's obvious what you want to do. Now you want to do the opposite, so to speak, and write the unitary as the exponential of whatever is there. So very different with everything that's made. So to do that, you need continuity. Remember that we explained, not proved in detail, but you can in the references you can find detailed proofs of all these statements. If you have, for instance, finite range interaction, in fact, much more generally, this group of automorphisms will be strongly continuous, and this implies it is a very simple one-line exercise. This is So continuous. So it means non-continuous. Then this unitary group of is simply continuous. This is nothing. You have to check the terminology. We're not familiar with it. So it means if you apply it to the vector, it's continuous. Okay. So, and then the Stone's theorem. Stone's theorem says that it's exactly the situation where you have a Hamiltonian that generates a unitary. Since density defined salvatory opposite H, yeah, like H omega now, to remind us for a little while that all these objects depend on the state omega I started from, such that this ut is e to the negative I H omega. Should these the boards. So we get a Hamiltonian. So that's what finds out about later in the space. And it generates the dynamics. You see, so we can help ourselves. We have to look at its spectrum, which is the energy spectrum of the system, of the infinite system. Energy generally of the infinite system we think of as infinite. So of course what has happened is that I've subtracted the constant energy so that this here will apply omega is equal to 0. So this vector state representing the state is an eigenstate with eigenvalue 0 of the Hamiltonian. And then the next thing I want to do is to look at the constant property. Tell me something more about this pattern. So here I look at something of the form omega A star delta A, of which I know is non-negative. And I'll write it as BT of if you want, I can do the representation. Then we'll have that's like that. U star T 5 omega equals UT omega. So this is the values of the vector omega. We're going to take t to 0. And we're going to define the generator with 1 over I. So that is delta, at least if A is in the domain. And now, of course, what I get here is the derivative of t to the omega divided by I at t equals 0. So this is 5 omega h omega. So it is the expectation of the Hamiltonian h omega in dense set of states 5 omega, and you know that all these are positive. So it means that h omega is negative definite. Okay. So circles in the spectrum is not negative definite. So we know that the spectrum of the right state then is between 0 to infinity. And what we mean by that state Okay, yeah. Here the system positive gamma. So that I have the square root of the union. I have zero at the bottom, and then the half of the so there is a gap, there is no spectrum in an interval 0 gamma. About the glasses. Yes?
But then this UT omega V may not be equal to omega V because then there may be some phase which doesn't affect the state and stuff.
Well, I mean, there isn't in this case because it's an eigenvector divided by 0. Well, it's an eigenvalue divided by 1 to t. So you take the derivative, 0. I mean, it's not that if I were to define I take another vector multiplied by a phase. So I have one state here only, so it's not going to matter. So there are one state at a time, yes, you can multiply by a phase and everything is.
Why did we assume that this has eigenvalues? Because it doesn't fall from the definition of the ground state.
No, but it follows from the unitary equivalence of GNS representations. Which I didn't prove this theorem. It's not very complicated. It's a constructive theorem, but it's a lot of time to do. I encourage you to go through it. It's nothing very sophisticated, but you have exactly these properties, and it follows from this property. Okay. So now we know what a gap ground state is. Now we can go back and see what it means for how you could formulate this algebraically. It's not like the GNS representation is something you usually actually construct. In some cases you can, it's one. Generally, it's not a complicated thing. There's a constructed procedure that involves dividing the algebra by some and so on. And so it's not something easy to carry out. In particular, you have to subtract the ground state energy, which you don't know, and so on. Okay, so let's give one more formulation. So this is sort of the direction we are expressing positivity, but I can also express a gap. So suppose for a moment that the kernel of the omega is just as one thing equal action. Then this additional gap it's equivalent to say that for every side in the plane of each of the atoms. We have the expectation here is one below one. So it's not just positive, it's actually bigger than gamma times the normal vector. If I take a vector, it's orthogonal to the gravitational space. And so this here is equivalent to saying that. So since I have that subspace, and it's sufficient to look at side of the form omega, which is that's in the Hilbert space, and of course side of omega is not it's the same thing as saying that omega in the plot is equal to 0, and this is the expectation of a state. And if I put this all together, so I can say that so there I think that as an E gamma. Okay, so there is the is gamma. All things, the main of delta is zero expectation. You can also use all A and subtract the expectation to get a slightly different result. Okay. So that's very useful. So again, it's a strength of the ground stability property. But now we have the right hand side, and that is positive. So this is the norm square of this guy. Now, if the equivalent is not on, so often in this field, when people study equivalence classes or constructing values, they assume you have a unique Algebra state. Then, of course, there cannot be an undefined because it is a useful representation. This would give a different expectation values to certain observables, and so this is true. As we'll see in the example, maybe it's a good to come to it. Some examples have many states, and some of them may actually be unitary equivalent and all sit together in one Hilbert space. Then the student is not contradiction, but of course you can do the same thing. You can just right, it's an equality for all A such that this vector here is in the orthogonal complement of the term. But it's not so easy to work it anymore because if you have just one, this you can this is equivalent to saying that for all delta greater than gamma omega t star to minus omega t. This is just orthogonalizing this side. So that you can do. But in the unique case, it's an algebraic creation of defining the capital state for an algebraic system. Okay. So far, so good. Right? No questions?
Can I ask something?
Yes?
How does this, I mean, we started with a local Hamiltonian and we did all sorts of constructions to eventually end up with H omega. Is it clear how this is related to the original local Hamiltonian direction?
Well, so yes, makes sense. So for A's in the domain of the Hamiltonian, this derivation is commutative with the Hamiltonian. For A's in the domain of delta, in fact, you can write the action of delta as commutative with the Hamiltonian. And then, so this is of course in the representation, but you can compute these commutators in the algebra. It's an algebraic thing. And so, yes, in this sense, it's very clear that if you have a local observable, you take the commutator in the algebra with all the terms in the Hamiltonian that don't compute with it, and you take the representative, you'll get actually the representative of delta. Yeah. However, it's very possible if you have different ground states, that you get different Hamiltonians. Well, in general, you have different Hilbert spaces. You won't even be able to meaningfully say that these Hamiltonians are the same or are different. But you can look at the spectrum, but in fact, the spectrum can also be different. Okay. All right. So maybe quickly. Yes.
Mark, this state, and though this formalism just probably looks like it's like in quantum mechanics.
Yes.
In fact, this it does mean that the state omega is pure.
Okay. I haven't said anything about that. So Peter introduced the notion of pure states versus mixed states. There's actually something important to say, maybe. So let's do that before transitioning.
There is actually a quick question from the Q&A.
Yes. Adjust the lighting. It looks dark, yes? So the other remark is that if we all talk at the same time, they can understand, but that's probably, yeah. There we don't have most of the time.
Is it in the chat?
Yes, it's in the chat.
Using the mouse to see what's the chat was.
So, yeah, adjusting the lighting, I did not, we tried,
No.
to do, and
No, sorry. That's not the question. I think it's in the Q&A panel, but I can read it for you.
yes. Sorry. Relation between H omega for different states omega and yes, okay. Again, there's definitely a relation. They are represent ground states of the same interaction. But are they unitarily equivalent, or is there some other connection like that? In some examples, maybe there are situations where you have unitarily equivalent ground states, or at least some of them are unitarily equivalent, but in general, then they can be quite different. And in fact, within a certain setup class of models, you can construct interactions that will have multiple ground states that you have chosen independent of each other. And then I would say, practically speaking, there is no relation. You can have interactions that have more or less any set of prescribed pure states and ground states. Okay.
Thank you.
Did you say that it happened that if you take two ground states of the same Hamiltonian, the same original Hamiltonian, that the resulting H omega could completely different spectrum?
I don't know what you mean by completely, but different.
Okay, yes, yeah.
They are positively or numbers, but
For the same original.
yes.
What about if the lattice is finite? Are they then equal?
No, for finite systems, this doesn't happen. All these representations are unitary equivalent. All ground states, the pure states. So I will come to pure states, are unitary equivalent, and no, it cannot happen in that case. Okay, so for finite systems, so usually if you have pure states as those defined by a vector, by an H, and mixed states by density matrices rho. And of course, this is a more general case that includes the pure case. So if I rank one projection on side, then that's represents a pure state and all other cases. It's a mixed state. So if it's not a rank one projection, it's at least rank two, and I can write it as a sum of two positive operators. If I normalize it, it becomes a convex combination of density. So not rank one. It exists density equations. One and two. And so T 60.01 plus the rho is T rho 1 plus 1 minus rho 2. So maybe it has is range of direction 2 and diagonals excluded eigenvectors, usually orthogonal, and I can write the general density matrix as the eigenvalue of first eigenvalue plus direct one of that eigenvector plus the other eigenvalue times the other one. Some of the eigenvalues which are non-negative has to be 1 because it's the density matrix, and so that's a complex combination. So that is the definition that the German provides. So the state omega is the it's pure if Non-trivial complex decomposition. What's the roots? What if we run? It's eta 1. Omega 1, 2 over 6. Say, we do, but a non-trivial combination would be if you write omega t omega 1 is 1 minus t omega 2. There's no non-trivial decomposition. It would mean that if you can do this with the t that is not trivial, then the states have to be identical. Okay, that's one way to say it. So that is what defines the pure state. But it's not decompositions like that. Either t is 1 or one of the states doesn't participate, or the two states are actually the same. That's pure, and the state is mixed, so it's not. Okay, so that's our example. So now, if you have a unique ground state, it's a pure state that tells you that happens when together with the representation, the GNS representation, the irreducible representation. So basically, the observables is really all of P of H, not the resemblance, right? You can close it in the proper way. You can show that the set of all ground states of a given interaction, given dynamic, so a given delta, and look at all the solutions of this inequality, the ground state inequality. Which maybe other ways. Out there. Yes, omega A star delta A equal to 0. I have a whole set of omega that satisfy that. So that set has some very nice properties. It's I think it has the property that if the state is in it and you decompose it, then the states that go into the decomposition are also ground states. So if you decompose a mixed ground state, the only thing that comes into it are ground states. And then the extreme points, you try to decompose it as much as possible. You get pure states with the reducible representations. There's more to say that the accidents of the dynamic speed that I'm referring to in my page references has a more detailed discussion. Okay. So we have defined ground states, GNS representation, and time flies, but I will nevertheless make some time for examples. Just to give you an idea. To give you the full sort of spectrum of possibilities, to give you lots of examples. You want to have time for that? But that's at least look at the LP model and the code model, square lattice. Mentioned it before, and Peter is discussing in great detail of one model, which he defined the Hamiltonian yesterday. So it's a finite link precision between Hamiltonian. I will not repeat it. all German professors are super window washers. I'm not, I'm just in a practice. So. So the feature. I didn't mention Corrales up about it, except that it was three-dimensional side of one-dimensional layers, and it is actually defined by the Lieb-Robinson interaction. Which means that by reaching to zero, unless x is of the form x plus 1. And in that case, it's given by a translate. So I'll not use indices here. So you know that this has to be an element of the local algebra, which is this pair of observables at x and x plus 1. And it's actually an orthogonal projection, which you can also write in terms of the spin matrices. So here you have x and x plus 1. And this orthogonal projection is the orthogonal projection in sign 5. It projects on the spin 2 states in the tensor product of 2 spin 1. So if you remember, that short series of SU2, 2 3-dimensional representations, tensor together, copies tensor together, decompose in 1-dimensional, 3-dimensional, and 5-dimensional one. This is the projection of the 5-dimensional. It's a translation-free model. So it's a unique formula. The state of AZ such that omega of this thing is x plus 1 is equal to 0. Right? So it's easy to see that a ground state, if you have something like this, and that's what I think Keeler already defined as frustration free. So Goldman also has it. And you can prove that there is only one state that is the ground state function. So there's no question that it's a pure state. GNS representation is going to be useful. The kernel of the Hamiltonian will be non-dimensional, and in fact, it's gapped. This was proved by, so this model introduced by Kennedy. In 1997, they proved that it's gapped. So it's striking. There's other things we can prove. As a gap, we are actually no map for the gap mathematically. We can remember exactly. But the best estimate is something like 0.1.
Sorry.
Yes.
I can't read this expression. What is the phi of the nearest neighbor? So the px, x plus 1.
So it's an orthogonal projection. I cannot P2 because it's the projection on the spin 2 states.
Yeah, and then it reads what after that?
The algebra of the observables of 2 spins, the one at x and x plus 1. Okay, but it's a translation variable, so it's phi. So translations. That is the interaction of the equality.
I think they wanted to.
Question is the expression in terms of spin operators.
Is there something?
We can't read the expression.
Times the identity
Product to the
spin vector at I, spin vector at I plus 1 was 6. 39 spin plus 1 squared.
Okay, it sounds like you had both of them explain them, so maybe it's fine.
But so maybe you can just say what's SX?
Oh, okay, right.
SX.
These are the spin matrices, which I also I think we didn't define.
Oh, it's really hard to see.
So the spin one matrices. Yes. So they have three by three analogs of the following matrices if you want. So there is an S6, which is this matrix. Then there's Y. Which is Y0 minus 9. And there is C. 1, 0, so. And then what I mean by this, it is the physics is not as high as the interaction. It's three things. So this is some alpha x y z as alpha x plus 1. This form is proportional actually to the representation of the number of the casting in this representation, and it's something that commutes with the representation. And this interaction has therefore the symmetry, since there is any ground state, this ground state will have the symmetry of simultaneous rotation of all spins under the action of SOP or SO2. And therefore, these by the theorem we just saw, these rotations are represented. So there is a interdimensional representation of SO2 that does the same thing with the genus. And there's some interesting things related to that. I'm trying to discuss. So that is the example of the EQT1.
Could you read again the formula now that you've explained what the spin matrices are? Could you read again the formula in terms of spin matrices of
Yes.
the interaction?
Let's. Okay.
Oh, well, that's a little high, but that's fine. It'll do.
Which you mean just which one I'm talking about?
The formula there in terms of the spin matrices, if just read it again, just say what it is. The interaction, right? There is formula for the interaction for the spin matrices because it's a little hard to read.
So it's 1/3 times the identity, it's a constant, plus 1/2 the Heisenberg interaction just defined, and plus 1/6 the square of the Heisenberg interaction.
Perfect. Thank you.
All right, sorry. Okay, so example B. On Z2. You know what I'm doing is station 3. So the set of the states consists of 4 equivalence classes for various notions of equivalence, particular unitary equivalence. So it's 1 in the vacuum. You want to make a 0, all that X up. And it's only 1 element in it. That's the unique frustration-free ground state and the 0 expectation to all the terms in the Hamiltonian. So in this sense, that part is similar to the EQT1, right? And that's again. And then you have the 3 infinite classes. So the electrically charged, magnetically charged, states that people introduce, and then you can also have those. But I'm going to call it the one that have diffuse charge absolutely. And all the things are infinite. So you can think of the pure states, the electric charge 1 as a copy of the space little to C2, because that charge is localized in the electronic code, simply localized, and then you can localize it anywhere in the lattice. And therefore you get a whole space of process. Same for magnetic, same for diffuse. Actually, I have two positions. So there are three infinite sets and one unique vector.
So you're talking about the equivalent classes of these states.
Right, so these are the non-point corresponding to the four super selection sectors that Peter was talking about. That is going to analyze
Unitary equivalence classes.
but within these classes, these are unitary equivalent sets. So I mean, you have to be a little careful. So I can define what these are. This is not a so for instance, when we do the thermodynamics, I want to construct ground state. We haven't started with ground state for a finite system. We take a weak star limit, we get a ground state of the infinite system. That's a theorem. But you have to be a little careful if you take weak star limits of ground states, you will get a ground state. These classes are not really close. But you can have a limit the vector state given vector, for instance. And in fact, in some sense, people use that to construct this class. I didn't say more about it. All right, so now it's really time to say a little bit more about locality and different ways of being more specific about the local properties of observables. But it's still 3 minutes, so let me maybe just get a preview. I'm going to use an interesting state to discuss that, and it'll actually be an important tool and the number of constructions that will follow when we study equivalence classes of gap states and automorphisms that are connected. And so this is the what I'm referring to, we want to make local approximations of our quasi-local observables. To do this, we're going to use the iteration state. I think I'm going to call it the whole special state. It is just a product state. And it just the normalized place. It is the density matrix that is a constant times the identity on each of the spins. And it's a product. If you have an observable that is a tensor product, like X and X as X plus 1, then this will and consider conditional expectations, which I can do because of the product state. Then we now in gamma, I will define pi of a gamma to this way, I consider a lambda as a surface of a figure. This lambda can be defined as not either way. The definition is that by lambda is the identity on the algebra A lambda. That's the restriction of the state rho is station state to the algebra the complement. And so operationally, what this means, if you have an observable or a bunch of tensor factors, some of which are lambda and some of which are not, you're going to take the partial trace by tracing all the factors that are outside of the lambda. And get something that acts as identity outside. It is more or less as close as you can get to the observable. Okay, so this is called the conditional expectation. There's also nice properties. And then it shows if you look at A minus pi lambda A norm, then take the limit lambda goes to gamma, and so what we get is a bunch of approximations of A. And in particular, if we take a sequence of lambdas that increase, maybe it's balls with fixed radius, then increasing radius. If you take a limit of the radius to infinity, you get A back, but you get a sequence of local approximations supported in balls of radius. And that's what we're going to use to construct some other algebraic observables, including the gate properties. And that will be for tomorrow. Thank you.